So in this presentation, I will explain a bit the domain that we're focusing on and how we addressed a solution, a possible solution, and the framework that we built. And also, I will explain as well the evaluation that we adopted. The first thing that I want to make sort of clear in advance is that I'm also a lecturer and I deal with computer science modules in higher education. So my students learn quite complex programming languages, and they need to obviously use the internet to gain knowledge about various topics. And the first thing that we encounter in terms of as students is that we need to retrieve information from online sources. And in order to retrieve information online from online resources, we used various techniques. So basically what we do, we create a query, we put the criteria that we want to search for, we put it in a search engine, and in here I'm referring to search engine not only on Google, but any application that exists online that can give us information back. It can be Google, it can be ChatGPT, it can be whatever gives you information. It can be just a text box, a search in a journal organization providing journal articles. And once we submit this query, the engine will pop up with various results. And we filter those results, we look into the results. If those results are valid, we actually click on the result and go forward. But if those results are not valid for us, we refine the query until we find the correct resources. So basically what we're trying to do is, that's why the arrows are bidirectional. What we're trying to do is creating an iterative process until we find what we're looking for. And some authors refer to this as the searching strategy, which is the approach a person takes in order to learn something or to get information. And we rely on various resources. The problem is that a good searching strategy requires various characteristics. And apart from, if I have to mention, some of them is patience, for example. You need to be patient until you find what you're looking for. You need to have time. Okay, so we cannot, in a way, help students, and maybe we can in some way to be more patient. We might teach them how to manage their time for time management, but also a very interesting requirement in a searching strategy is prior domain knowledge. And that means that if you know nothing about the domain, you won't be, or you will find it a bit challenging to ask a question about the domain in order to retrieve information. So the more you know about the domain, the more your questions, the answers that you receive from a search engine will be more relevant. Okay, so that is very important. And unfortunately, novice students, so students that are in the first year, for example, won't have knowledge about the domain, won't know what the domain is about. So their search queries or their search information will be a bit limited. Their query will not be as effective as one that is in the third year. So what we're trying to do is, we're trying to use machine learning, which are basic statistical models that try to learn patterns and trends, try to learn and map these searching strategies. And what we're looking here is next word prediction. And basically what it is, it's a very simple concept because, and we're all used to it, because whenever we type a message and we send an SMS, the system will suggest that with what should go next, and then you decide what you want in reality. Next word prediction is based on time series, so having a series of one after the other. The time series prediction is that you divide that into smaller sections, and then try to understand, try to forecast based on the past actions. So that's what we are actually looking for. So this were our research methodology. This is our research methodology and how we adopted it. So basically what we did was that we wanted an application that can actually capture behavior that is happening on the internet. So we're talking about searching something in Google, searching something in ChatGPT, downloading a paper, visiting a website, internet activity. And then, based on that internet activity, we train algorithms to learn what a search strategy is. How people, basically, how our students, how lecturers, whoever is using this system is searching information online. So the algorithm will learn that. And once we collected all the data, we ended up with a lot of data because we search a lot on the internet. And we did feature engineering. We identified which parts are important and which are less important. And then we used it to evaluate algorithms and determine which algorithm should be used in this aspect. So basically how it works as an overview. So let's say that we implemented a Google Chrome extension. So it's a small application that you install in your Google Chrome. Most probably everyone is familiar with. And basically this just collects the history or the searches or the clicks that you're doing online, basically. And if a lecturer installs this application and the student installs this application as well, it's capturing data from both of them. So the collaborative framework, which resides online, is collecting this data, and it's making sense out of it. In fact, for example, to mention a few examples, extracting data was not a big issue, because whenever you search something in Google or whenever you search something online, the URL that you submit at the top, it will include actually the search that you're trying to do. In fact, for example, all those three, you have a search in Google, a search in Stack Overflow, and a search in Wikipedia. All those three are searching for the term machine learning. So it was not very difficult to extract the data. So what we did was we sort of investigated various machine learning algorithms. We took 12 in consideration. They are all, I'm not going to go into details on what they are and the hyperparameters that we fine-tuned, but they are all mentioned in the paper that I submitted in this conference. And we use what we call a grid search approach. A grid search approach means that brute forcing these algorithms, you fine-tune them. So you start changing the parameters until you obtain good results. So imagine you have 12 algorithms, and on a sequence, you're trying them all until you identify the best one. In our case, it was the best three, just not to rely on one in particular. And I will explain why later on, because we wanted to build a voting system. So having an even number, it doesn't make sense in reality. So how it works. I'm not going to go into the technical details, but basically, in here we have a sequence of what a student searched in an hour. So we grab the history for each student, and we built this sequence, this time series. And then we split that time series into our slots, 1 hour slots. We just chose an hour just not to have a lot of data, and it showed in reality that 1 hour is ideal, because if you extend it to 4 hours, students can go and search for something, and then 2 hours later continue searching on something completely different. So 1 hour is more or less reasonable. So this is a sequence of a student that in an hour he searched for these terms. For example, machine learning, artificial intelligence, data science, supervised learning. The next one is a website that he actually visited, and then he searched also 2 other terms. It is important to note that once this sequence was included, was captured and stored in a central database, we created subsequences out of it. And what does that mean? It means that a machine learning algorithm requires training, and training involves giving, if it is supervised, giving a set of inputs, giving an output, and you tell the machine learning algorithm, I'm expecting that if you have this input, I'm expecting that you predict this output. So I'm training the machine learning algorithm. And in this case, we can see as the blue key phrase as the input. So if we're training sequences, if we're predicting trends, I'm expecting the machine learning algorithm says that if someone searches machine learning, the prediction will be artificial intelligence, because another student, that's what he searched next. Okay? So this is like a one-to-one. But since machine learning algorithms, if you have a lot of time to train them, can actually take more inputs than actually one, you can also take in consideration many more previous actions. So here we're saying, given the first input, the second input, and the third input, I'm expecting to give me an output of this. So it is important to note at this point that the machine learning algorithms are not taking in consideration just if I give you A, you need to give me B. It's taking in consideration if I give you A, give me B. But if I give you A and B, I'm expecting C. If I'm giving you A, B, and C, I'm expecting D. So it's a sequence. And in fact, there are various algorithms like long short-term memory, LSTMs, that are designed for these type of sequences. And we just wanted to identify from what there is available, the best three that there are based on our data. One of the things that we actually implement, that we actually took as an approach is, or maybe the question that might pop out is, how did you determine which algorithm is the best? And in order to do that, we used precision recurrent F1 scores. That basically, these are accuracy measures that they do not rely only the accuracy, the traditional accuracy rely on the number of actions that were predicted correct by the algorithm divided by the total number of actions. But these are taking in consideration the true positives and the false positives or true negatives. So, all right, you predicted this as A. Is it really A? Or you predicted this as B, but is it really B? So these three equations basically take care of that. So that is the approach that we took to determine the best three. We noticed as well that as data changed, the best algorithm was always also changing. So if with 1,000 rows of data, linear regression was the best algorithm, once we had 2,000, another algorithm kicked in. And when we increased again, linear regression kicked in. So it was the algorithm that was used, the machine learning algorithm, is highly dependent on how data is changing. So we cannot say just, okay, Omar's discovered that 1, 2, 3 are the best. We implemented it there and it will be there forever. It needs to be a bit dynamic. And in order to cater for that, what we did was that whenever the system starts, it will execute the training process, and it will decide by itself which three are the best. Once it determines which three are the best, it will plug them automatically into the system. For those familiar with programming, for those not, I will try to explain a bit. Nowadays, these machine learning algorithms are providing common interfaces. So if you learn how to develop one, you know how to develop more or less every one of them. Thank you. So all algorithms proved promising It depends on the data that you have, basically. So we implemented that as well. And as a framework, when we implemented the framework, what we did is this. So a student searches something. The action, visiting a website, whatever it is captured by the API, which resides online, and then it passes to the prediction engine. The prediction engine will will extract the sequence, what the student searched in the last hour, okay, including the current one, and it will give it to all these three algorithms to give their best shot. The three algorithms will reply with a prediction. And then there will be a voting mechanism that will decide which prediction should be presented to the user, to the student back. So maybe I did not mention the Chrome extension is not only capturing the data, but it's also displaying the results. Okay. The voting mechanism is very, very simple. It works on basic voting system, so the majority wins. And if all three predict different results, we rely on the confidence of the algorithm, how confident it is the algorithm to present that result. If they have equal confidence, we just give all the three results, and then the user decides where to go. So basically, that's how it works. Here I have an example of, for example, a student searched machine learning, and the system predicted other topics that goes beyond a bit that, or maybe more in detail, more granular, that he might be interested in. So we have supervised learning, deep learning, neural network, training data, testing data, feature select. They are all topics under the umbrella of machine learning. And when we dig deeper on from where this was captured, so we ask, how did the algorithm learn about this? We noticed that it learned during a machine learning lecture. So the lecturer was delivering a lecture, mentioning all these stuff. And students were actually Google them and taking notes immediately of the short description that Google displays. So automatically the algorithm learned that all these are correlated to each other. Another thing that I challenged a bit the system is ClickHouse. ClickHouse is a database engine that is quite new in the industry right now. And we include it in the module, in our modules, because it's been used in the industry in Malta a lot. So we wanted students to be prepared for it. Unfortunately, the lecturer was not prepared for it as well. So it was a new concept for him as well. So I actually typed ClickHouse database, and it presented various, decimal numbers. It's not related, but for example, that is open source, that it's a column-based database. Those are all true. Okay, and then we said from where it learned, and we noticed that it learned while the lecturer was preparing for the lesson. So the data was captured from there. I'm not going to mention all good things about the framework. I'm going to mention even the bad things. For example, here I said I'm going to challenge it a bit more, and I mentioned materialized view, which is a bit more challenging in terms of ClickHouse. The results are all more or less related, but they are a bit generic. So if the system does not know about that topic, obviously, it will try to give the best shot. Okay, how we evaluated this? I'll try to be quick. How we evaluated this? We created two tests, multiple choice, not to have closed answers. We give the first test. We had a sample of 11 students. We give them the first test related to ClickHouse to know their current knowledge on ClickHouse, so we can remove any bias. And then we divided the classroom in two. We told the first half, which will act as the control group, to use the internet to search, to answer the questions of the second test, and the evaluation group to answer the same test, but using the internet plus our application. Once we got the results, we removed the first result from the second one. So we made them all, how to say it, remove the bias basically. And what it showed was the bias was not that high. In fact, the average mark of the first test was 2% and 7%. So they didn't have any knowledge of it. But it showed clearly that the difference, those students that used the framework that we're proposing, they obtained good results, and it's like 82% against 52%. And the reason behind that is because they were exposed to key phrases that were not available to the other students. Some pros and cons, knowledge gain. So as we've seen, it provides pedagogical benefit. The mark shows it all in reality, or all right, the classroom was a bit small, so as a future enhancement, we need to evaluate it more, but in a timed assessment of 20 to 25 minutes, it already showed improvement. Students were motivated a lot about having a system that is providing where to go next. It helped novice students because they didn't know anything about the domain, and they got 82% against the 52. The only two concerns that we had was privacy. To be honest with you, when I told students that you need to install this to extract what you're searching for, they all said it's a big no. But then when I explained to them when the application, you close it, it does not capture anything. And the benefit that it has, they actually contributed to volunteer to participate. And one of the other drawbacks that we have is unseen data. So if the algorithm is not trained on data, it won't predict anything in reality. It needs someone to train it. But we're using an assumption that a lecturer will prepare the lesson and capture some data from there before it's actually being presented to students. One last thing, futures. I said it 2 times this. Future research opportunities.
So that's the last one.
Okay. Future research opportunities. We have a lot of data. We're helping students. Our next step is help the lecturer. And in fact, we are trying to create dashboards. And we are trying to extract analytical out of this. So the lecturer will, for example, learn about the domain coverage. How much the student searched about this. We're trying to go there, but it's still work in progress. Thank you very much.
Thank you, Omar.